Okay, so hello everyone, welcome. I am Josh, and I'll be talking about, as you already know since you're here, Introduction to Procedural Sound Generation using the Web Audio API. So, just so I get an idea of background, how many of you are familiar with procedural audio? Okay, close to, well, yeah, half. And exactly half a person, so half people. And how many of you are familiar with the Web Audio API? Two. Okay, pretty good. What's your knowledge of Web Audio API?
I use it for the speech synthesizers and for some simple sounds in the app.
Okay, and yourself?
Just some basic synthesis, very basic.
Okay, so well, what I'll be doing is talking through what procedural audio is. Most of you know, or half of you. The web, and I'll be using Web Audio API to demonstrate how to construct sound procedurally. So sounds generated in algorithms that one might use in a game for primarily for sound effects, but also for music and for speech. And we'll kind of try to build it from the ground up so that people who have never used the Web Audio API would have sufficient knowledge to at least get started and know where to look for more information. So building hello world apps and then talking through, after the basics, some of the more advanced things that one needs in order to make anything more than just beats and tones. Scheduling of sound, so developing envelopes, attack, decay, sustain, release type envelopes, and worklets that allow you to really do any sort of processing with sound that you might want. Because the Web Audio API is actually fairly minimalist, but it can be extended to do a very wide variety of things. There'll be demos throughout, and we'll look at creating something more realistic. So creating explosion sounds, and then lots of sound effect demos for lots of different sounds that one uses very often in games, such as footstep sounds, for instance. So to back up, what's non-procedural sound in games? The traditional game audio is based on a data-driven model, large libraries of pre-recorded sounds. So you need footsteps, somebody has recorded footstep sounds. You need a dragon roaring, somebody has recorded a lion roaring, or something close to it. And these samples are then associated with objects or events in the game. So when a player fires a gun, we call up a gunshot sound, it gets slightly modified and rendered. This whole model is very different, of course, from the way animation is done in modern games. It's like the graphics in Myst, which was a massively important game from 1993, but the way in which Myst worked for its graphics is it had 2,500 static images, so like photographs, flat renderings, and it would simply call up each one for each scene. And can you imagine if all animation was done that way? Vast libraries of photos, find the photo closest to what is wanted for a particular frame in time, and that's what you use. And that's basically how traditional game sound works. So procedural audio goes in a different direction. For those from a more signal processing engineering math background, it's very similar to sound synthesis. And the first occurrence that I found of the term procedural audio was about 10 or 15 years ago, and in some works by Andy Farnell. And I know Andy well, so I asked him one time, did you come up with the term? And he said yes, he was trying to get people in the games community interested in the idea of algorithmically generating sound. And he was talking to them about sound synthesis. No one in the games community liked the term. Synthesis sounded artificial, going away from something seeming immersive and real. So he used procedural audio, which, because games are all about procedures, people latched onto the idea. But it's basically thinking of sound as a process, like a recipe for generating sound, rather than the end product, rather than the sequence of numbers that correspond to a waveform. So nonlinear, often synthetic sound, created in real time, in a very interactive, adaptive sense, according to algorithms and via input from gameplay or any other case. The advantages of this are quite a lot. You can create new sounds that have never been recorded. If you want the sound of a dragon roaring, you can build a model of a dragon. There's no libraries required, so the games don't need massive amounts of storage. There's no issues related to royalty, related to editing the files in the game. There are, however, equivalent, different issues that come up, because you then need to find the right models, you need to adapt the models and so on. But there are inherent advantages as well, such as the sounds being unique. So many of the different procedural audio techniques use noise sources. Random stochastic sounds being, or random stochastic signals being part of the sound, which means that every time the sound is generated, it's slightly different. So inherently, the sound is not repetitive. Code can be built into objects, features can be modified at runtime, and like a lot of graphics, when you have two objects interacting, you have the properties of their interaction stored with the object. So in theory, with procedural audio, you have the properties of the sounds that the objects will generate when they interact together. So it's a whole different paradigm. It has actually been around for quite some time. The very first games used, with any sound, used sounds generated by simple synthesis of oscillators. They didn't store recorded samples because they didn't have much storage. But it's still a fairly new idea for modern games trying to deliver whole auditory worlds. Very high quality sound, very diverse sound. And there's a lot of resistance to it, partly because the quality isn't yet there, but also new approaches are needed, new tools are needed, a lot of effort. Hopefully, once all of those things have been achieved, we'll be able to make sounds that are far more interactive, far more diverse. So that's the idea, but how can we implement it? And for that, I'm going to show things using the Web Audio API. So the most common ways in which procedural audio is implemented is for prototyping using things like pure data or max MSP, and then potentially VST instruments written in C++, or plugins for game audio development middleware such as Wise or Fmod. But the Web Audio API is built for web applications, for games and any sort of application using audio that runs in the browser. So it's not back-end, it's directly in the browser, embedded as JavaScript. The paradigm it uses is signal flow development environment. So like LabVIEW, you might be familiar with, or Simulink, which is part of MATLAB. Unreal has Blueprint, and Pure Data and Max MSP I've mentioned. So these are all, those ones are all graphical flow data programming languages. The difference with the Web Audio API is a subset of JavaScript, but the main difference is that it is text-based. So at the moment, there are some tools, very limited, for visualizing what is going on as data flow. But there's no development environment for the Web Audio API where you work fully in a graphical sense. So how does it work? Well, you define nodes. These can be sources of sounds, they can be filters, they can be effects, and we'll talk about how to add your own versions. You connect them together and output to media files that get played out or directly to the audio output, the speakers on a laptop or whatever it might be. And by connecting them together, you're also processing and manipulating the audio. So in effect, the whole system is always running. You might turn on or off the sound, the user might interact with certain components to change values, but it's always running. A few basic terms before we get to the point of developing the sort of simplest Hello World application. So audio operations are handled inside an audio context. One needs to define the context, and then when any audio operation that is performed, you refer to that context. That way it's possible to have multiple contexts, say something operating, two different audio streams happening at the same time. And within a context, all the audio operations are performed on the audio nodes, and there are really only three main types of audio nodes. So there are the sources, a simple tone, a noise source, potentially, a recorded audio file. There's all the processing, stereo processing, spatialization, interaction that might occur in between, and there's the destinations. What is the output? Saving it to a file, playing it out from loudspeakers. And then building connections between them, and not shown here is modifying the parameters of the audio nodes. So I'll go through all of the possible nodes there are built into the Web Audio API. I can do that because, like I said, it's quite minimalist. The types of source nodes are media elements, and so recorded audio or media streamed audio, and a scheduled source, of which you can have a buffer. So, say 1 second of audio, say there's data, not on the file, but maybe directly in the code. You can have a constant source, so continual value of 1 or 0, and you can have an oscillator. Various types of oscillators are built in: square waves, sawtooth waves, triangle waves, and sinusoids. And that's it. So there is no inherent noise source or any of the more fanciful noise sources, any of the more fanciful sources you can think of. All of the processing is just these 12 types right here. There's the bicod filter, which is standard or not quite standard filters, low pass, high pass filters, slightly different implementations than the most standard ones. They're there. A convolver for applying reverb, a wave shaper for, say, creating distortion, simple delay, a compressor and other dynamics processing, a gain, simply changing the level of a signal, and an IEEE filter node, which you can't change the parameters of. So it's very, once you set this for, say, a high-order complicated filter, you can't interact with it, you can't change the parameters. So as an API, it has flaws, but it is being improved, and I could see at some point in future things like the IIO filter node being replaced with something that is more interactive. Spatial processing, you can position the listener. You can take multiple channels, left and right, merge them into one, or take one channel and split it into several. You can pan the audio left and right, and you can pan the audio in any way, and you have one that's very specific to stereo panning. And you can apply things like HRTS, immerse someone in the world. The destinations, as I've mentioned, you can specify the standard or audio destination. You can specify a media stream that it can go to. And there's also a destination that it can produce output after that destination, which is an analyzer node. So to present, say, an FFT, a spectrogram of the signal, or just signal level over time. So we can move on to a hello world. Can you all see this, by the way? Okay, so It's only a few lines of code. That's the way all hello world should be. First thing one does is simply define a context. So context is going to be the new audio context. All the audio processing will happen within that context. Then to create the nodes, you simply say for that context, I create an oscillator or a gain. So the oscillator will be by default. If I don't specify otherwise, it's going to be a sine wave. The gain by default has an amplitude of 1, so it's not doing anything. So every node that is created has its default value, also has minimum and maximum values for the parameters. Then there are two ways to set the parameters to new values. Either you create the node and then specify that for that node volume, the gain value has a value of 0.25, or else you can set the parameter at the point in which you define a gain node. So volume is a new gain node for that context, and the gain has been set this way. The source nodes that were mentioned, so the oscillators and the constants, they need to be started. By default, you create it, but it's not actually producing any output until you specify it to start, and so you can start it and stop it. So we would get no output from this until we specify that the tone should start. And then you connect the two nodes together. So it's not a lot of code. Here's how the whole thing looks. And one more point to mention is of the popular browsers, not all of them have implemented all of the features of the web audio API yet. Although it is a major part of HTML5, it is still an evolving standard, not fully supported. Chrome have done the most support. I think the Chrome team are doing the most development of it, so they have a vested interest in doing the most support for it as well. So you can pretty much guarantee that everything in the API will be in the Chrome browser, but with the others, 90%, 99%, and of course that's no good if you're developing an application and 99% of the lines of code that you write work and 1% don't. Okay, so let's hear this hello world. So, here it is again, and let's see. Now, a few problems with the speakers here, so it's probably just going to play out of my laptop, but I think you should hear it fine. So all it did is produce a simple tone with default values. And there's no interaction, there's nothing in the interface. So, extend it just a little bit to have some more interaction. It's good practice whenever using JavaScript and the web audio API is to separate the interface, so the HTML code, from the algorithm itself, the JavaScript, so two files. So we have one where here I'm just using default things built into HTML5 for your user interface widgets. So we create two sliders, one for the frequency of the tone that we create, one for the gain of the tone that we create. And we have the same code as before, but now we get the frequency value, we get the gain value, and we update the frequency and the gain of our audio nodes whenever the user interacts with them. So, let's see. And that's it for the hello world, but how can we do anything more interesting than that? So, not a lot is built in. There's a lot of, if you use any of these signal flow, especially audio-related signal flow development environments that I mentioned, there are some standard things that almost always occur. How do you add two signals together? How do you multiply signals? How putting a constant in? And so these are all done in a few lines of code. Because I've been doing a lot of things with the Web Audio API, made them all functions and just called those functions over and over. Adding two signals together, you can take two signals, input A, input B, connect them to the same output. You can think of the outputs as sort of like buses on a mixing console, if you're familiar with audio processing, where any signals you put into them just add together. To subtract one signal by another, you take a signal that has a gain, you create a gain node, set that gain to -1, and you invert gain. You connect a signal to that gain node, that automatically multiplies it by -1. Multiplying two signals together, you have a gain node, so it has a signal, it has the gain applied to that signal. It doesn't matter which signal is which, but they end up multiplying together. So take two inputs and connect them to a gain node, one as the main signal, the other as the gain on that node. Similarly, with using the constant sources, you can add constant values and subtract constant values, multiply them as well, same idea. So to do something a little more complicated, this is an example of an audio effect. So processing an audio signal using the Web Audio API, one can have a delay with feedback. So it takes an audio signal, delays it by so many samples, and feeds that back to the original in a feedback loop, so you can use it for echo and slapback type effects. So a very simple type of reverb can be implemented this way as well. So here we have 5 different nodes. So we're going to create all of those nodes. We set the values of each of those nodes. The delay one has a delay value associated with it. We have gains for the feedback, for the dry gain, so dry meaning the input signal does not get processed and goes straight back to the output, and the wet one for the processed or delayed version of the input. So create the nodes, set their values, and set up the connections. It doesn't matter, by the way, which order these two steps are in. Once things are being connected, they are running virtually instantaneously from that point. So, the sequence doesn't matter. The only thing that matters, of course, is you need to define the variables first. So at that point, we're quite limited, not just in terms of the types of signals that can be done, or that can be created, but also in terms of how one can manipulate the parameters of those signals. So I can change the gain, but how do I do automation? How do I have that gain curve changing over time? How can I create an envelope on a signal, have it die down over time? So we look for a minute at parameters and their timing. All of these different nodes have parameters associated with them. For a gain node, you have a gain. For a constant source, you have its offset value, essentially the value of that constant, how much it's offset from 0. For a tone, you have its frequency value, and the type of, for an oscillator, you have a frequency and the type of oscillator it is, a square wave or a sine wave. So each of the audio parameters can be changed by setting them, which is what we've done so far, connecting a node to them. So if a gain connects to a tone's frequency, not to the tone itself, but to its frequency parameter, then we'll be multiplying that frequency parameter by whatever the gain is. And by scheduling events. So parameters have a list of events. We're going to look at this on the next slide. And we can say schedule a parameter to ramp from one value to another value over a certain amount of time. And so we can apply these automation curves. So that way you can get the nice ringing sound of a bell.
I don't know if it's okay to ask questions.
Yes, please do.
Can you go back one slide?
Mm-hmm.
This is not a sophisticated question. I just didn't know what you were talking about. You were saying it doesn't, the order of what you do doesn't matter within, I must have missed something, but within what context? The order of what?
Yeah. So there's a few things that are almost always done in setting up the graph.
Okay.
You define all of the nodes.
And that must be first, I would imagine.
Yeah, well, yeah, you define a node before it's used, but on the other hand, you don't need to define this wet level node until down here. So you can define everything else, and then at a later point in time, you can add a new node to the graph.
I see.
But the main point I was saying is there's a few things that are always done. Creating the nodes, setting their values. You can actually set the values when you define them as well. And set up the connections between them. You can also have the scheduling that has been mentioned, or that I'm about to talk about. The order in which you set each of these elements of how to construct this graph doesn't matter. So there's a few things that can be done with the parameter scheduling. We can set a value at a given time. You can get from the system clock what the time is now and say 1 second from now this value is going to jump to 0. Or you can say I want it to jump to 0 at this moment. There's a few things that I haven't shown because they're not interesting, so you can clear any scheduled values, reset everything to its initial value. You can have a linear ramp to a value at a time. So you change from whatever the value is now to a new value at some time in future. So you have a gain that is 1. You say over the next 1 second it's going to ramp down to 0. The ramping can be linear or exponential, and it's a bit tricky because they have two ways of doing the exponential, but you'll see what I'm talking about over the next couple of slides. One way is to say that it's going to, just the same way as the linear ramp from 0 to 1, it's going to ramp exponentially from 0 to 1. So you'll have a curve that goes like that, or a curve that goes like that. And it's given by the equation that is shown. Just the important thing to note here is that at time t1, the result is exactly whatever the value v1, your new value that you want it's going to be. The other way of doing exponential ramping, so an exponential attack or decay, is that it approaches the value that you want, but never reaches it completely. So you want it to ramp down at a certain rate, but it'll take forever because it's decaying exponentially, take forever to reach that final value. And so that's setting a target at a time. So from the start time, you're going to move towards a value of 0 at a rate given by a certain time constant. And then the last form of parameter scheduling is to set a value curve at a time, where you store, say, 1,000 values, complicated set of values for any function, or can come or random, and the parameter will follow those values, that array, over the time that's specified. So this is an example of sort of all of the ramping possibilities that can be done. Setting a value at a given time, and then linearly ramping that value, exponentially decaying it, where it's approaching a value of 0.5 but never completely reaches it, and then exponentially increasing, exponentially decreasing again, And finally, set values to match a particular curve, in this case, the positive half of a sine wave. So the code for this is one of the more complicated things that's built into the web audio API, but once you get the hang of it, then it's pretty straightforward. The code for this is simply setting all of these values at a given time, and calling the functions that were mentioned on the previous slide. So set value at time, we say at time t0, we're going to set the value of this parameter p to 0.2. Yeah.
Okay. Please stop me if there are too many questions.
No, I love questions. They're so much better than listening to me.
Untrue, but I have a question, which is, can you contextualize this in a game audio example? Like what these different, like the linear, I guess, like the linear curve, the attack decay versus the exponential. Is there some, can you provide an example where you would want these different curves inside of it?
So, I'll provide a lot of examples later, but I guess it's very useful to have some context right now while I'm going through this. And an interesting thing here is we can use these values over different time scales. So on the one hand, you can have an impact sound, and that decays over 50 milliseconds. And we can set this to decay over a very short time scale. Even though it's operating within the browser, we have sufficient accuracy to model the type of behavior of the decay of a bell ringing. But you could also have things continually generated footstep sounds as a character is moving off into the distance. And so you could apply a gain on top of the whole. If things were in pure data or max MSP, it would be a subpatch. But a whole block of code in the audio graph, you could apply a gain to it that is very slowly being ramped down as a character takes 10 seconds to move away.
Can I just have a quick follow-up?
Yeah.
So in the example of the bell ringing or the sort of knock on the table, would that be a linear ramp down or an exponential ramp down?
Generally, real world, they're almost always exponential.
Mm-hmm.
But sometimes it's just going to sound better to be linear. Or, of course, if you have someone moving off into the distance, that's linear, the power of the sound decaying linearly. So because it's power, it's actually a square. But what we hear sounds like a linear one. So, well, I'll play a sound example right now, and you'll hear the difference between a linear and an exponential decay. And you can hear that although a linear decay is not how things would occur in many natural situations, when someone rings a bell, almost always the modes decay in some form of exponential rate, it can be very useful. Otherwise, the sound just feels like it goes away too quickly. So, why don't I do that? Let's see. So this isn't my doing. You can find it online. Someone else's code for creating different sound envelopes and seeing what they look like within the web audio API. But we have a sound. I think it's a simple tone, and it's going to have a gain applied to that based on this automation code. So I'll change. So you can't really see much. A very short, like 10 millisecond, 10 millisecond attack, decay, sustain, content value, and then release. So I'll change the release to an exponential. And that changes, you can probably barely see it, changes the scheduling on that parameter from a linear ramp to an exponential ramp, and changes the sound like this. So I'll do it one more time, but back the other way. So you can all hear the difference there. So yeah, I'll give more practical examples once I kind of finish going through the basics. Okay, so I mentioned there's 18 different types of audio nodes, and that's not enough. It really doesn't compare with other audio processing based in signal flow. So there's probably 30 or 40 different objects in pure data. And one of the things that my research team and I have been trying to do is to have all the functionality of pure data within the web audio API. Because an awful lot of procedural audio has been done within that environment. If we can bring it over to the web audio API, we can do a lot of great procedural audio on the web. So the default nodes are not enough. A few examples. There's no noise source. You can't just have pure noise. And virtually any sound synthesis is going to want a noise source. The filters themselves that are built in, so the low-pass filter to remove the high frequencies, they're not the standard ones. Almost every other software package that has some audio processing or just signal processing, filtering built into it, uses slightly different filter designs than they do, which means everything's going to sound slightly different. So you'd rather have your own filter. There's many other objects that are built into different development environments that are standard there, which means if you're going to port something over, there's no web audio analog for that. And any other processing, you've created some crazy, funky way to distort a sound, you'd like that. So a few years ago, when it was in the early stages of web audio development, they had something called a script processor. But it wasn't really running within the audio context. And so it was using the same timing, the same memory allocation as things on the interface, on the user interface, which is creating lots of problems. Over the last couple of years, they've replaced it with audio worklets, which is really a proper analog of the audio nodes for creating your own node. So the simple example, let's build a noise generator. These audio worklets, they can have any number of input signals coming in. Those signals can each have any number of channels. So you can have 3 signals, each of which have a left and right channel, or 5.1 stereo, 6 channels, however you want to do it. So there's a very rich in terms of what can be done. The same type of behavior for the outputs as well. And they default to processing 128 samples of audio at a time. So that and also the default sample rate for the web audio API is 48 kilohertz. So you do have a few milliseconds of delay. You do something on the interface, there's a minimum 128 samples delay to process and get some output, which is actually very good considering all of the other timing issues related to doing things in the browser. The timing issues are generally not coming from the web audio API, they'll come from other things. So what we have right here is a simple noise generator. You register a processor, call it noise source, which is an extension of the audio worklet processor. You have a constructor. I'll talk you through these steps. Here I just define output as the output, so there's 0th signal, 0th channel, and then for every one of the samples, they are equal to 2 times a random number minus 1. So why did I do it like that? So it's a random number between -1 and 1, because the random number in JavaScript is only between 0 and 1. So the superconstructor is just the way that these processors in JavaScript work. They require the superconstructor in there. It's not really used for anything in standard worklets. Here we've referred to the signal and the channel. So the arrows are a little bit offset, but the signal and the channel for that signal. And the processor itself must return true, or else it kills it and it's not doing anything at the end. So that's the basic code for creating the audio worklet. And one other thing, the worklet must be in a separate file from where it's used. I don't remember the full reason for this, but it does create problem. Well, the standard, the API doesn't allow them to be in the same file. So you can create a new file, worklets JavaScript, with the worklet itself, and then you call that file from your main JavaScript file. So here we simply say we add a module for, we add the worklets file, we create a new source based on a definition for the noise worklet, and we connect that noise to the destination. When you create your own audio worklet, you don't need to start it, it starts automatically. So, add module loads the audio worklet, and then we just create the user-defined audio node. So let's see what that does. Why is that doing that? Okay. So that's it. That is a simple noise source, which is not doing anything interesting at the moment, but that's all the code that you need in order to create nodes that are not built into the Web Audio API. It can quickly get complicated, but once you've got the basic building blocks, it's a lot of repetition. And once you have, say, worklets for the processing you use over and over, you can save them and reuse them, of course. So the low-pass filter is actually, I come from a signal processing background, so I tend to emphasize this. The low-pass filter is a second-order one, whereas the standard low-pass filter, the one used in teaching, the one used as the basic building block, is a first-order one. Everything will sound different, and they're not equivalent. If you change the parameters in the second-order filter they use, you don't get the standard first-order low-pass filter. So, here we have the code for an audio worklet that will do a low-pass filter. As the standard one. And it's just translating a few lines of math into JavaScript, but a few things beyond the noise. For the noise, we didn't have any parameters whatsoever, just produced a basic random noise signal, so random values between -1 and 1. But here, for the low-pass filter, you specify some cutoff frequency where we are removing all of a signal, or as much as we can of a signal beyond that value. So you need parameter descriptors, where you define a parameter frequency, you set it to a default value, in this case 100 Hertz. And every parameter that you come up with has optionally a default value, a minimum value, and a maximum value. You don't need to use them all, but it's built in addition to the name of that parameter, of course. For this filter, because it has feedback in it, within the constructor, we define from some variables specific to the worklet. So we have a last out, it takes that last out value, feeds that back into the input, and with the gain applied, that's what gives us filtering of a signal. And it has this line of code is actually the operation that filters the signal. The output channel is equal to the input times the coefficient plus 1 minus that coefficient value, where the coefficient came from the frequency, times whatever was the last output value. And as mentioned before, the worklet itself is in a different file from the main code where you are building the audio graph. And here, you need to set the parameters of the worklet, of the low-pass filter. But otherwise, it's similar in implementation to the noise worklet that was shown. So, one more example. So, I have noise again, but now with the filter applied. And compare that with without the filter. And sounds pretty horrible, but you can hear that the signal has been filtered. So up to this point, it's basic programming. It hasn't been much that is gain specific. But you have enough skills at, once you know these initial levels, to start doing the more fanciful things. So let's start off. I went through kind of all of the different sound effects we've been building in the Web Audio API and tried to find one or two that were good as sort of the next stage after the hello world. Explosion sounds. Fairly simple to start creating something sounding at least a little bit realistic with what we've covered so far. So, to create an explosion, a bomb, a grenade, some explosion with water being sprayed, or a gaseous or boomy one, it's mainly taking noise sources, filtering it, and shaping the envelope. So you get a very quick attack, and then a decay, and a now burst of sound, filtering the sound so it emphasizes more low, more high frequencies. And that's it. So the core connections are creating a noise source using an audio worklet, applying an envelope using the scheduling that we've covered, and filtering the signal using something like that low-pass filter, which you can use the built-in filters or create your own filters to do so. And then the connections are just noise connected to the envelope connected to the filter connected to the output. In order to create more varied versions of this, you have multiple different noise sources, same operations, combine them together. So this is what the full audio graph looks like for an explosion sound generator that I'll show in a couple of minutes. I left out one or two things at the end to sort of enhance it, or say when you filter a signal to then apply a bit more gain so it's not much quieter than the original signal. It uses, in addition to the white noise, it uses pink noise, which is just filtered white noise, where more of the frequency content is over the mid-range, the range of speech. It doesn't sound like all high-frequency hiss. So we use a pink noise, low-pass filter to get the really boomy sound. We use pink noise without additional filtering to get primarily the mid-range sound, also some high frequencies, and white noise to get a strong emphasis on the high frequencies. We apply a gain to each of them, and envelopes to each of them, and that's going to be the output. Does it look like you're about to?
Yes, I do. I'm dying. So on the other slide, why was, I have a vague concept of what an envelope is. Can you just explain, pretend like I know nothing, and explain what the envelope is in this case? I didn't really understand why the envelope was going in before the filter. There's some clear...
Yeah. So on this slide?
Yes.
Okay. It doesn't matter which comes first, filter or envelope.
Okay.
There is dynamics processing that will affect the filtering in some subtle cases, but that's more like the math of the signal processing. In general, these two sets don't matter. So the envelope, we use that to change the signal's waveform in time, where really it's like a volume change, like someone riding the faders, varying the volume. on a sound source. And the filter is, of course, modifying the pitch and filtering the spectrum. So so we use the same paradigm for explosions to build whoosh sound effects, where there's one more thing that's done, which is having that jump from left to right. But basically, if we want a sort of a spray sound or something like that, it can decay over a certain time. It can decay linearly or exponentially. And it might emphasize very high frequencies. So if there's a car rushes past you over gravel, you might get more high frequencies than a big truck or lorry going down the road past you. So you filter it for the type of sound that you want. You modify the envelope, but there isn't much more that needs to be done.
Does the envelope describe the graph, I don't know what, the function that we were creating before it was strange looking, but with the attacks and decays?
Yeah. So I didn't give, I didn't even give an informal definition of envelope. So it is that usually, but not always referring to a gain, but it is a change in a parameter over time. So in this case, and this is the most common case where the sound designers are referring to envelope, they are referring to level changes over time in whatever the signal is, often automated. So rather than having to go like this for 20 seconds, if you're modifying the level of 20 seconds, you draw out a curve and whatever the tool is, that curve is your envelope. And so whatever signal goes through gets a gain, sample by sample gain, as it goes through that envelope. So in what I showed before, there was about 4 seconds with an attack, decay, sustain, release. That's the envelope that's applied to whatever signal. We had just a tone, but by applying an attack, decay, sustain, release, we make it into a sort of a ringing sound. If you make it very quick, a quick attack and then short decay, you make it more like a beep.
So an envelope, that describes then, like if we have like a set of repeating, like we repeat these attacks and decays, this set of function, I guess, for lack of a better word. The envelope describes the entire length of the process and the sub-process, or the image that we saw, the short image, or is the envelope the smallest peak, is the smallest unit of repeating?
Okay, here it's not referring to repeating.
Okay.
If you do things in the browser, then if you want something to repeat, the most standard way to do it is, I think it's an HTML5 function, but it's called set interval. And so it's not audio specific. It's like if you do something terrible, like have the web page flashing at you every second. There's built-in JavaScript to do that. So it calls a function, so it repeats with whatever is the system call. But you can have your function be an envelope that's applied, and then on top of that you have this repeat there. So I'll give you a quick example of one where we did that. Okay. So we're applying reverb to a signal to give it a sort of echoey sound, and we apply an envelope, so it's a ping sound, but then we're using the set interval function that's part of JavaScript HTML5 to have it repeat once a second or so. But because the audio graph is set up, then you can modify, it's always running, so you can modify parameters, you can do things interactively and change the sound. So that would be a very strange submarine ping, but you get the idea. And it's not a lot of code to do this. Once it's there, it's in place. So there's a tremendous amount of overhead for the interface and the fact that this has all these other bells and whistles on the side, like applying new reverb and panning and things. But the core code for this here is probably about 25 lines of code. And that's really just sort of tweaking the envelope and the repetition and things like that. The graph itself is still a very small one. So that's probably, oh yeah, so the explosion, I'll return to it for, not for much, and we're almost at the point of showing lots of demos. So this is not going to be the best explosion, but it shows what can be done with just 3 noise sources, filtering them, and applying some sort of time-varying gain change or envelope function. So the core things that are done are generating or defining the noise sources, where not shown we have pink noise, which is a filtered version of white noise. We make connections. So our low frequency noise passes through a filter. The filter then has an envelope, which we call the low end gain, and connects to the low input, which is the input to the final output. So our low frequency content goes to the output. We do the same thing for the pink noise covering the mid-range and the white noise covering the high frequencies. And applying the envelopes, we do it by setting a value at a particular time. So it jumps up, it's an explosion, so the attack sounds almost instantaneous. Jumps up to a very high value. We've applied a huge gain here, and that's because we also filter the signal an extreme amount to keep only low frequencies, and when you do that, you've removed most of the energy in the signal, and so you've made it very quiet. And then we say, okay, we're going to exponentially decay the signal towards 0 with a certain time constant. So it never actually reaches 0, but it exponentially decays that way. And we do that same sort of application of envelopes for the mid-range and the high range. So let's listen to and look at what the explosion is like. And this is where using the speakers in the room would make a big difference in impressing you, but doesn't change your knowledge of things. And you can see the parameters here, a low gain, a low decay, so the decay rate of the exponential, and the sort of weighting, amplitude weighting of how much of it is low frequency content. And then the mid-range is over here, it's the pink, and the high frequencies are in the middle. Adding a few more things that weren't in the code that was shown, so some distortion of the signal to make it sound gritty. So another explosion, if we want explosion on water, you get a sort of a splash sound to go with it. Okay, so at this point, that's basically the core skills that are needed. So I'll do a lot of demonstrations of sound effects that have been built using the Web Audio API and intended for use for procedural game sound. So we have a website, where everything is fully procedural sound effects. Even we're not using wavetables. We are not using automation curves of stored data. The curves will still be combinations of sine functions and things like that. And it has 56 sound synthesis models, 374 presets for specific sounds, and it's sort of increasing all the time. Simon, you might remember a bit of my inaugural lecture, so it's doubled in size since then. The long-term goal is to get it to the point where you don't need sample libraries at all anymore. So maybe that's too ambitious. Maybe machine learning, we can learn millions of presets rather than a few hundred presets. But that is the dream that we're trying to reach with it. So here is going to be a good point for some audience interaction. So this is the system I was talking about. Here's all the different sort of models we have: engine sounds, droid sounds, applause, beats, there's footsteps, and so on. So I'll take a risk and ask for someone to suggest which sound they'd like to hear. And I bet you will go for the one that has the biggest bug. I don't know which one that is, but sound. Ricochet. Okay. The interesting thing about that one is it was one of the first ones that we did, and so I don't know where it came from. I want to keep it because I think it sounds interesting, but I don't know. I mean, I know the code. I don't know why the code is doing what it does. But it emphasizes the ricochet type sound of a blast, a gunshot, or something, but really gets the sound to it. So. And it has a sort of random variation every time it's hit. So it's very much a sort of cartoon sound. You're not aiming for realism, you're aiming for exaggeration. Another one? Friction?
Yeah.
Okay, you picked one that we are in the process of changing right now, and it's definitely going to have issues. It's based on something called the Sound Design Toolkit, which was developed by David Riccesso and other researchers working with him, and in Max MSP and C++. So we've looked at that code, which is all open source, tried to port it over here. Let's try. Okay, so that's more of a ceramic plate wobble. A braking car. A metal bowl wobbling. So I think it's got elements of the types of sounds that we're looking for, but it's a work in progress, that one. Let's see, so I'll suggest one, not because I think it's great, but because it's always given as an example of where procedural audio could really benefit games. So we happen to be particularly well attuned to hearing footsteps, our own and anybody else who's walking along. I have lousy hearing, but I can still tell if someone is about 20 meters behind me, wearing high-heeled shoes, and what surface they are walking on. I might not be able to tell what they're saying, but I can hear a lot in their footsteps. And the example that's given is in a typical first-person shooter, you might need the sounds of a dozen different characters walking on a dozen different surfaces, different sounds for left or right feet. The early games that had footstep sounds, it sounded like everyone had 2 left feet or 2 right feet, and you need some natural variation in each of them. And so pretty soon you're using a good chunk of the game's storage space just for the footstep sounds. So you can model the footsteps. And high heels. Running in grass. Changing the shoe. So, what's going on here? Well, we use that repetition, the set interval that I mentioned that's moved in JavaScript to repeat the sound over and over. We have an impact sound that is just a pure noise source, but then with an envelope, so it's lasting over the period of time that a foot hits the ground, with some filtering applied. I think it's 2 noise sources in quick succession for the ball and the heel of the foot. We do one for left and right. Most of what makes the sound realistic, or even close to realistic, is getting the timing right. That's just as, if not more important, than getting the frequency shaping right. And then...
Sorry. Timing in this big
Yeah. So, for instance, I played the sonar ping sound, and then I varied it just by making the intervals much quicker.
Okay, so setting the interval time.
Yeah.
I see.
Yeah, and for, we have applause as well, which I'll play later. But for the applause sound, you can get one hand clap right, and that's no problem. But it doesn't sound like applause until you have the right amount of synchronicity between all of the hand clap sounds that you're generating. So it's something that's overlooked in a lot of the audio signal processing and things, which concentrates on how do you get the spectrum right, but to make things sound realistic, it's how do you get the timing of all of the different components of the sound as well. So yeah, what's going on here? How do we jump from our sort of hello world examples in the beginning to something where even if it doesn't sound right, it's far more sophisticated and closer to what might be usable in a commercial game? It's still based on a few basic source nodes, some timing for changes of the parameters, and some basic processing on each end. Now there can be some stereo processing. There are nodes for panning and so on. But a lot of it is the filtering and the envelopes that are being applied. So when you change things here, some of them are changing presets. We know we will filter differently for different surfaces. We will change the timing between walking and running. But otherwise, not that much is changing. And then the actual shape of the envelope is dependent on the heel, how much you roll, moving from between the ball of the foot and the heel of the foot. And so we have some parameters to sort of shape the shoe that is applied and the nature of each footstep. But it's just fine-tuning the envelopes that are applied there. So maybe here's a good point as well to encourage questions, comments, criticism. So anything that you would like to know about the procedural audio or web audio API.
You have a lot of presets. From what I understood, I think you said you've doubled since Simon last saw this.
Yeah, although to be fair, that was a while ago.
How are you finding them?
Yeah. So sometimes trial and error, sometimes serendipity. A lot of it has been analyzing samples, so sort of manually listening to a sample and playing around with parameters. Once we've built the model, playing around with parameters until we match it, or using analysis and visualization tools, or even our own code to extract features. So say the average value, or the range of values, or the spectral centroid. Using features from spectral centroid just means like the sort of the center of pitch of the signal. To extract them from the sample, and to extract them from recordings of the sounds that we produce. So to use this optimization to get that to match. So I'll give you an example. So most of what's here, it was all developed in the Web Audio API using what the tutorial is about, but most of it was developed by students working with me. And an unfortunate thing about academia is no matter how much you try to prevent it from happening, students keep graduating. And I try, but they graduate. And so eventually all the students working on this left, which meant that if anything more was going to be done on it, I had to do it. And I didn't have any of the skills that they did. So I tried teaching myself with a few sounds that I thought would be simple to do. And bell sounds I thought are fairly simple because it's just a few frequencies that are most of the sound that are, they all appear at close to the same time. They all decay exponentially. It's finding those frequencies, finding out how long each one takes to decay, find out their initial amplitude, and you've got most of the bell. And so I found a nice recording of Big Ben, which I thought, I'm just going to adjust the interface slightly. Okay, that should be big enough. Which I thought, well, that's appropriate. Currently, it's under renovation, so you can't hear it chiming if you're in central London. And of course, it's an iconic, well-known sound. And so I used various things to analyze the signal from Big Ben and then try and implement that in this procedural audio model of bell sounds that I was creating. And so I played the output from the online system, from Effective for it, and I played the bell sound. And I realized, oh, I'd made a mistake because they sounded the same. So I must have played the same sound twice, either the synthesized sound twice or the original bell sound twice. But after a bit more investigating, I realized, no, for the first time ever in my life, I wrote a bit of code without it having loads of bugs in it the first time. First time ever, I'm not that young anymore, but first time ever it worked properly the first time. So there were actually some issues in the very beginning onset of the sound, but I knew that I hadn't tried to fix that. So here's hopefully the sound. This is the 6 o'clock news. No, but yeah, that's exactly how it sounded in a recording of Big Ben. And if it wasn't playing from those speakers, you would realize that it's still decaying. You'd still be hearing that in the room. So the large bells, the envelope lasts for quite a few seconds, not just 100 milliseconds or something like that.
So did you pick bells because you had an idea of what that model would look like, and then you're learning and then I keep thinking of it in the context of some sort of machine learning, but like you had the model in mind and then you were adjusting the parameters, or?
It really has been a bit of all options. So we started off because the most well-known body of procedural audio models for generating sort of the game sounds is the work by Andy Farnell for the book Designing the Sound, where he's got gunshots and footsteps and everything that he thought would be nice to have in a game. And so we thought, can we extend that to the point where it's just not the first 25 models that he could come up with for games, but where we can replicate all the sounds in sound effect libraries. And we got a grant to do it as an online service. So we started with existing models, porting them to Web Audio API. Some of them already had presets. So the first way we do it is whatever we can find that's already available. The second way is sound designers, professional sound designers who we were working with say, this is the type of sound that we often use, which you don't have, whoosh sounds. And we thought that's interesting because we hadn't developed any of the models for abstract sounds onomatopoeia. Everyone knows what they mean by the word whoosh, but it's not associated with any specific thing that it must be associated with. And The bell sounds, and a few like them, were because I thought I'd know how to implement it, or another researcher working with me thought they would know. So one researcher is very interested in, say, doing dragon sounds, so he's going to do that just for fun. The presets are based on the fact that the sample libraries, what we would like to replace, are some of the best examples of the sounds that sound designers will use. And some of these sample libraries have tens of thousands of sounds. So they're a really good resource. If you want to synthesize an arrow hitting a piece of wood, you'll find 100 examples in there. You can start extracting features, you can apply machine learning techniques, clustering, and get a sense of what are the features that represent that class of sounds. And so the presets, some of them, as mentioned, were serendipitous, but some of them are based on analyzing examples that you can find in sample libraries. So I'll just show you one recent one. We started analyzing and found a sort of approach to recreating bird tweets sounds and the simple whistles. And once we had it, then we could churn it out as an assembly line, and we have 36 presets of different bird sounds. So it's not that the model can generate 36 sounds, rather these are 36 sounds within what it can generate. Ideally, and this is the benefit of procedural audio, it goes far beyond what any sample library will have, because that only has a finite number of sounds, whereas a procedural approach has however many ways you can vary the exposed parameters.
Can we actually hear that?
Yeah, but let's see. So this is one where it sounds synthesized, but there are a few neat tricks that you can do to make it sound more realistic. So first off, it sounds synthesized not because it's wrong, but this is what these birds, their tweets, would sound like if they were recorded in an anechoic chamber. So you're not getting any sort of natural reverb. So if we add some reverb in there, no idea if this is a good one, but you get something starting to sound a little more natural world. And also, when you listen to real-world recordings, they're not in isolation. You get the wind rustling through the trees, you get the distortion from the microphone and everything else going on in there. And so you get additional noise and random variation beyond just the bird's voice itself. But yeah, so these are based on analyzing each of these bird sounds, figuring out some common values in the recording that are what we expose on the interface, and then analyzing the signal to find those values and put them back in. So for procedural audio that is using game sound, what approaches are done? So there was the session yesterday, for music and sound, where there were a few talks about sort of procedural music generation, algorithmic music generation. And so the music is not sort of synthesizing the musical instruments, but rather the composition and the score in those cases. So a different type of approach. And there's speech synthesis as well. But for the sound effects, you have physical models where a lot of them are sort of recreating the entire physics of the world, and then looking at, well, what is this artificial world produces sound at the end? Which in most contexts is complete overkill, but in games is not necessarily overkill, because you might already be creating that world. So there's the physical models, there's what a lot of these are sort of signal-based approaches. We find that combining a few oscillators, filtering them, applying a compressor to them, starts to sound like a helicopter or whatever it might be. And so it's a bit of guesswork, a bit of modifying of the signals to do it. And there's sample-based approaches, which are not purely procedural. They can be, to a large extent, procedural, but they start with samples like granular synthesis, break them up, recombine them to create new sounds. So when you see procedural audio implemented in games, it can be any of them or a combination of them. And machine learning can be applied to optimize the parameter settings within them, or to generate new sounds, or to match what it's doing to the game context.
Just a follow-up on that. So how good are the objective functions or fitness functions if you're doing it with machine learning? So to optimize it, you've got to have an objective, which could be trying to match the envelope, trying to match that central pitch that you mentioned. So do you do it as a multi-objective optimization problem, or?
Yeah, it is. But the matching the objective, or finding that minimum for the objective function is not.
No, I really mean how easy is it to formulate the objective function in the first place?
Okay, yeah. So that's where I was heading.
Yeah.
Minimizing it is not the problem. Yeah. Formulating it is the problem. So you hit the nail on the head right there. So we've had a few papers about that sort of thing, and it's a big open question. What makes a gunshot sound different, like from a hand clap? Not just physically, not just perceptually, but in terms of the signal, what are those features? Because you can have an infinite range of features to work with in order to comprise an objective function, or more problematic, you might only use spectral features, and yet that particular signal, the perception of it is dominated by the dynamics features. So how do you choose the set of features to combine into an objective function? If we analyze lots of samples, we can cluster them, we can look at what are the common features and values, we can apply some form of component analysis to figure, or random forest to reduce the number of features that one needs to work with. And so we can look at clustering to identify the important acoustical features for each sound class and then form an objective function based on those features. So in the work that we did, we looked at maybe a half dozen or so proposed objective functions, or we created an objective function based on a set of features that someone had said would be a very strong candidate. And what we found was that none of them was working a lot. Some were working, some were very poor choices, but there were none that were consistently great choices. So we were looking at trying to create environmental sounds based on what was going on. And we used some quite well-known ones that have been applied for music or for speech context. But if we wanted to find something that, a set of features that would allow us to recreate the sound of running water in a stream, or rain sounds, or wind sounds, then minimizing one objective function when we then did a listening test with human subjects, they didn't agree with that objective function, and they might prefer something else. Or the objective function that would perform best for one rain sound would not perform best for a different recording. They were each better than random, but there was clearly a lot more work to do. Yeah?
So question, we have quite some sound effects in this tool. How portable is it? Just is it on all browsers? Or does it already hit the portability issues between the browsers?
Look, what do you mean, portability?
So you said that web audio was not supported through all browsers. Does it run on all browsers? Or does it already have issues?
Yeah, so the portability is mainly a question of the browsers kind of catching up.
Yeah,
it's not, it's not like
it will never
happen on Microsoft where it's a question of it's good enough that most of the models will produce sound of what we have here in Firefox. a bit less will do it in Edge. Safari is on probably an equivalent level to Firefox in terms of how much they implemented. But then, say there will be something that we have, the applying reverb, that might fail on Firefox. So that means that there's one feature that will work on
Yeah,
music.
so this already has some issues.
And those problems are not specific to this. So if you look at the forums of other people developing great keyboards or music synthesizers, they'll run into similar issues with multiple implementations. On the other hand, though, I've yet to find anything that works on my laptop but not on my phone. So the Chrome problem or Chrome functionality is portable from device to device.
Yeah.
You had a question?
Go ahead. No, please. All right. So, what is the status of like a generation of audio based on some nonlinear models? Like, is like, let's say, multivariate, like time series analysis, like LSTM or something like that. Is there anything like generating wind of this repeatable sound? Do you have any?
Yeah. It's a really big question.
Okay.
In the sense of what is the status of using a wide variety or whole class of algorithms for the...
No, sure, of course, but it's like you clearly have decided to go into it in a different direction, right? And there must be a reason, I'm assuming, right?
Yeah. So abstract sound synthesis where one just sort of wants to create an interesting pattern. I've seen techniques based on fractals, based on Markov chains, loads of different algorithms. I'm not sure of any that has widespread use. But some of them are quite good for getting variations on something. So you might have a piece of music that you can apply some non-linear processing to get those interesting variations on it. Here, we have an intent. We want it to sound like a real bird. So we're not going to use some of those other algorithms for it. For the physical models, they generally, some of them will embed the physics directly. So if you want the sound of a bouncing ball, you use Newton's equations of motion to predict things. Others will do that sort of create a whole artificial world. So time difference. So ones where sort of grid up the space and look at the interaction between coupled oscillators in that space. But for the general area of what you're asking about, what I think, if I understand it, is lots of different things have been proposed. I haven't seen any as sort of an established So variations on a sound, I've seen lots of different algorithms, but even not anyone that's found it.
Okay.
I guess to your point.
Okay.
What's that?
Yeah, I was asking. I guess like probably some of us have tried like for like in the context of BCG to generate. I mean, I have done with students like I've used multivariate LSTM to try to produce or reproduce like rain and fire and stuff like that based on like frequency representation, so like spectral representation where like the different signals were actually, and so but that didn't work very well. And so I was asking whether...
So something that's produced some very impressive things have been DeepMind wave nets.
Yeah.
Or yeah, the Usenet is actually pretty impressive.
Yeah.
Like that's why.
Oh yeah.
Who knows?
So the speech synthesis, the deep learning techniques have really taken off and have surpassed what were essentially sample-based approaches of the last few years, and that's completely changed there. And I've seen really good ways to replicate audio effects using deep learning. And yeah, WaveNet is extremely popular. The current limitation, I won't say it's always a limitation, but at least one thing that makes them very challenging is you could have the sound of applause, you can run those samples through the system and get something regenerates applause, and then you can make the sample longer, but or louder, or change the pitch, or have an infinite variation on it. But how do you control it using perceptually or gain state specific parameters? How do you say, I want to change the number of people in the audience generating applause from 18 to 1800?
One of the example that I've seen in this sense is that, for instance, I've seen an application of Max for racing games in a company. Actually, if you want to make the acceleration run, this is actually very difficult if you don't do it procedurally, because otherwise you should have a complete library of sounds to reproduce that based on the fact that your user might change the input and speed of the pedal, stuff like this.
Yeah.
So you can actually reproduce this pretty easily with the networks, with neural networks, but you actually cannot have the input of the user that if it does like this, it should do run. And
Yeah. Well, you might have something that changes some sort of abstract parameter, but how do you say, I want it to change from a 6-cylinder to an 8-cylinder?
Yeah.
Any last questions? I think time is just about up. So in which case I will play one last sound for you, which so you don't have to do it. It doesn't sound very good over the speakers, but of all the sounds that we've run through perceptual listening tests, this was the one that sounded closest to the real thing. We compared it against 5 other algorithms out there, and we were almost indistinguishable from the real thing, whereas the others were far from it.
I guess that here it's very difficult to make the avalanche effect, because there is actually there are mathematical models of the effect. If I say, oh, let's go, nobody applauds, then we're all still, and somebody like this, and then there is basically a progression in how the people applaud. It's not like we want to say 1, 2, 3, 1, 2, 3.
And there's also the synchronization, and sometimes you get a spontaneous synchronization where a crowded amphitheater and everyone is sort of applauding at exactly the same time.
I think we should applaud Josh.
That sounded much more realistic. Thanks very much.
Thanks. Great. Glad we got coffee.